So our next speaker is Péter Pál Pach, who talks on coloring the smooth numbers, coloring in the British sense and not the American spelling.
Thank you. So I will talk about the coloring question, on which I started to think more than 10, almost 15 years ago, and it's still widely open. So I thought I would take the opportunity and advertise it here. And it's a joint work with Andrés Caicedo and Thomas Chartier. So first, I will show a problem that was the original motivation for the question, which is the topic of my talk. It's motivated by a problem in coding theory as the following question. If A is a finite set of, say, positive integers, is it true that if you take the symmetric difference of the n sets A, 2A, NA, then the size of the symmetric difference is always at least n. So here 2 times A means that we multiply each element of A by 2, etc. So just to see an example, if n is 3 and A is the set of the first 3 positive integers, then 2 times A is 2, 4, 6. 3A is 3, 6, 9. The symmetric difference is the set of those elements that appear in an odd number of the sets. So in this specific case, the symmetric difference of the 3 sets turns out to be the set of the first 3 square numbers. So its size is at least 3, which means that in this specific case, the conjecture holds. And the question which is the topic of this talk is the following one. It is a separate question for every positive integer n. And we ask whether it is possible to color the positive integers by n colors in such a way that for every A, the numbers A, 2A, 3A, NA all have distinct colors. So for each n, we take this question, and we will say that a coloring is n-satisfactory if it satisfies this property. The connection with the previous question is the following. If a set A has an odd number of elements, and there is an n-satisfactory coloring, then the size of the symmetric difference is indeed at least n. So we need an n-satisfactory coloring, but we also need that the size of A should be odd. And the proof is really quick because we can also think of the symmetric difference of A, 2A, NA in the following way. Let the element of A be A1, A2, AK. Then in these n sets, for each AI, we will have AI, 2AI, and so on, NAI. So let's collect these n tuples into sets BI. And the symmetric difference of the original n sets is the same as the symmetric difference of these sets. But in each set BI, there is exactly one green element, if green is one of the colors that we use in the unsatisfactory coloring. So we are taking the symmetric difference of an odd number of sets, each of which contain exactly one green element. So at the end, in the symmetric difference, there will be at least one green element, and this also holds for the other colors. So this was the connection with Pilz's question. But there is also a connection with the conjecture of Graham, namely the following one. Graham conjectured back in 1970 that if n is a positive integers and we take n positive integers, then it is always possible to choose 2 of them, AI and AJ, such that AI divided by the greatest common divisor of AI and AJ is at least n. So for instance, if we take the first n positive integers, then we have equality, but there is another example where we do have equality. For instance, if you have 4 numbers, so n is 4 and the numbers are 2, 3, 4, and 6, then if we calculate all these ratios, then we get the numbers from 1 to 4. And indeed, the largest one is at least 4. So Graham's conjecture also holds in this specific case. And in fact, Graham's conjecture holds in all of the cases, as it was proved by Balasubramanian and Sundararajan. If there is an n-1 satisfactory coloring, then this would mean that Graham's conjecture holds for n equals m. So this would give a new proof of Graham's conjecture if there would be an n-satisfactory coloring for every n. Here again, the proof is really quick. Let's take m numbers, b1, b2, bm, and we take 2 of them, bi and bj. Let's write g for that greatest common divisor, and we take a satisfactory n-1 coloring. And since this coloring is n-1 satisfactory, we get that the color of bi and bj must be different if Graham's conjecture would be false in this case, since they are both contained in a set of the form G, 2G, 3G, n-1G. So any 2 of them have different colors, which is not possible because we have m numbers and only n-1 colors. To highlight this connection in a bit more detail, let's define a graph with the vertex beating the set of the positive integers. In this graph, let us connect 2 numbers, I and j, if and only if the larger one among them divided by their GCD is at most n. So this is an infinite graph on the set of the positive integers, which contains a lot of cliques. For instance, 1 to n is a clique of size n, but 2, 4, 6 to n is another clique of size n. Graham's conjecture states that the clique number of this graph is n. It's clear that it is at least n, since we have a lot of cliques of size n. Graham's conjecture stated that the clique number is just n, and the existence of an n-satisfactory coloring would mean that the chromatic number of this graph is also only n. So if there is an n-satisfactory coloring for every n, then this question should be more difficult than the Graham's conjecture, because Graham's conjecture is a corollary of this. Okay, let me continue with some partial results. First of all, with this graph formulation, we can concentrate on the connected components of this graph. And it is not difficult to see that all these connected components are isomorphic to each other. And one of them is the one which is spanned by the n-smooth numbers. So let's write Kn, the set of those positive integers that are n-smooth, so they do not have prime factors larger than n. They form one of the connected components, and clearly if we can color one connected component, and if all the other connected components are isomorphic to this one, then there is a good n coloring of the whole graph. So once again, for instance, K5, but also K6 is the set of the numbers that have prime factors 2, 3, or 5. And now we will only study whether the set of n-smooth numbers can be colored by n colors in an n-satisfactory way. Yes, let's start with a small example, which is not the smallest one. So let n be 4. We can actually, so here we have 2 prime factors, 2 and 3, and we will use the integer grid to collect the 3 smooth or 4 smooth numbers. The x coordinate tells us the exponent of 2, the y-coordinate tells us the exponent of 3. And here in this quadrant, we have all the 4 smooth numbers. The property that the coloring is force satisfactory states that each translate of this polyomino contains 4 entries with different colors. So 1, 2, 4, and 3, for instance, and in the translates A, 2A, 4A, and 3A right there. Okay, let's try to find the force satisfactory coloring. Here is an element A, and because of this style, because of this L shape, here we must use all the 4 colors. And now we will figure out the color of 6A. Because of this red translate, the color of 6A must be different from the color of 3A. And because of another translate, this blue one, the color of 6A should also be different from the colors of 2A and 4A. So only one possibility is left. The color of 6A must be the same as the color of A. And now from the blue translate, we learn that the color of 8A should be the same as the color of 3A. And we can continue filling out the colors, and we get such a pattern. And it is not difficult to check that this coloring, which is uniquely determined, is indeed force satisfactory. Let's take a look at the color classes that we find here. So here I collected the 4 color classes, and if you look at it for a while, you can notice a pattern. Namely, the color classes are the residue classes mod 5. The residue class of 0 is missing. We color only the 4 smooth numbers. And it is really easy to check that this coloring is indeed fine. And also, instead of 5, we can take any other prime. So if P is a prime, then by defining the color of a P-1 smooth number A to be its residue mod P, we get a P-1 satisfactory coloring. The color classes are the non-zero residue classes mod P, and it is immediate to check that this is indeed P-1 satisfactory. So at least for infinitely many values of n, there is indeed an n-satisfactory coloring. This is the case if n is 1 less than a prime number. In fact, this specific case was the one through which Andres Caicedo, one of my co-authors, learned about this question, because when I thought on this problem and realized after some time that I felt that I couldn't make more progress, I started to pose some specific cases in the Hungarian math journal COP, which was founded back in the 19th century.
All right, Peter, we've lost audio.
Yeah, I think you muted yourself by accident or something.
Can you hear me now?
Yes.
Oh, sorry. Thanks. Okay. So I posed this problem in COMA, which is a more than 100-year math journal for high school students. And if you look at the name of the students who managed to solve it, you might find some familiar names depending on your area. Then Péter Pál Pach saw this problem in COMA and posed it on Math Overflow, where Andres read it and suggested it to his student Tommy Chartier, who is not on this picture. but on the next one. You can check his performance on YouTube if you're interested, maybe after the talks only. So getting back to the problem, if n+1 is a prime, then the answer is affirmative. And the idea of this construction can be pushed a little further. Namely, if 2n+1 happens to be a prime, then there is also an unsatisfactory coloring. Here we use the quadratic residues mod p as the color classes. So we use the non-zero squares, and here again it is easy to check that the coloring is fine. And at this point, it is natural to generalize the idea further. If P is a prime of the form k times n+1, and the first n case powers have distinct residues mod P, then the coloring which assigns the residue a to the k mod P to the n smooth number a is unsatisfactory. So the number of non-zero case powers mod P is exactly n, and we want these to be presented as the residues of the first n case powers. If k is 1 or 2, then this holds in all of the cases. So this is satisfied automatically. But if you try it with, for instance, 3, then this is not the case anymore. Here, looking at the smallest cases, we notice that there will be equal residues in these cases. And in fact, it can be proved that if we try this kind of construction with primes of the form 3n+1, then this will never work. So there will be always 2 cubes that have the same residue. So it is not possible that the first n cubes have distinct residues mod 3n+1 if P is a prime. This is also a problem that I posed in Kuma back then. So for n+1 and 2n+1, it was a success story. With 3n+1, we didn't get any new constructions, but for larger values of k, it is still possible that this condition holds. In this case, we say that the prime P is a strong representative of order n. If for a certain n we can find a strong representative, then there is an unsatisfactory coloring. So for instance, there is a 7 satisfactory coloring using the prime 659, and there are also some other examples. For instance, 24 was not yet covered by the previous results. So in certain cases, these strong representatives do exist, but they are rare. And the reason behind this is that if k is larger than 2, then there can be only finitely many primes, such that kn+1 is a prime, which is a strong representative of order n.
Does this hold any connection whatsoever to the germane type conditions? This has something of a familiar ring. This the generalizing.
There might be. I'm not sure. So I should think about it. There may be such a connection. Anyway, so the number theoretic properties of n are certainly very important regarding this problem, and yes, there can be such connections. I'm not sure. I think I skipped the proof of this statement because I would like to show something else. So let's get back to
Just sorry to distract you again.
Yes. Mhm.
The number of I mean, this is a very particular construction for satisfactory colorings.
Mhm, mhm.
It is from what you've seen, does the number of satisfactory colorings grow with n, behave very non-monotonically with n? I mean, this is very sensitive to the particular nature of n, but the number of actual n satisfactory colorings might be growing, very quickly with n.
Probably if for n there is there is an unsatisfactory coloring, then it's probably growing. We studied this in the first few cases. Of course, here by the number of colorings, we should mean the number of colorings of the n smooth numbers, because if you color all the yes, so probably it's growing, but what we did is just we looked at the very small cases regarding n, and it seems to be slightly growing, but this is just the first 10 values, so I wouldn't formulate any conjectures regarding the number of colorings, especially since for 100% of the values of n, we don't even know whether at least one such coloring exists or not. Okay, and now I switch to a different point of view. Again, we looked at these 4 satisfactory colorings, and it's not difficult to get that that coloring can be defined with the help of this formula. And instead of this linear form alpha plus 3 beta, we can try to generalize this. So we take the primes up to n, we choose some coefficients, and if this mapping happens to be injective on the set of first and positive integers, then it is easy to see that there is an satisfactory coloring. And if n is relatively small, then there are a lot of prime numbers up to n, which is helpful in this case, and one can easily find suitable coefficients. So here, in fact, what you need is a coloring which is something like a discrete logarithm, because the condition which should hold is that whenever I and j are 2 numbers not larger than n, such that their product is still at most n, then the color of I times j should be the sum of I and j. So we have a partial graph of a multiplication table of the cyclic group like this, and the task is to extend it to the multiplication group of say the cyclic group. In this case of 4 satisfactory colorings, this can be done in a unique way, and whenever this can be done, then there is an unsatisfactory coloring. So this is the case for 4. This, in fact, generalizes the idea of strong representatives. They call these colorings multiplicative. And with the help of this idea, one can also show that if n is of the form p squared minus p, then there is also an unsatisfactory coloring. In fact, instead of the cyclic group Zn, one can use any other abelian group. So whenever the partial multiplication table can be extended to a multiplication table of an abelian group, then there is an unsatisfactory coloring. But according to the result of Fourcade and Pollington, this is not the case always. So there exist numbers, for instance, 195 is such a number where this group theoretic approach doesn't work. it is not possible to extend this partial multiplication table into the complete multiplication table of an abelian group. So all the constructions that I mentioned in my talk can be obtained with this method. And according to the result of Orchard and Pollington, for instance, for 195, this is not possible. So either there is no good coloring at all, or a new kind of construction is needed in this case. And to conclude my talk, I'll just give a summary of the known results. So there are these 3 infinite families where it is known that there is an unsatisfactory coloring. And if n is very small, then can we check that unsatisfactory coloring exists? The first open case is 195. But if you look at this sequence which contains those integers for which this group theoretic coloring doesn't work, you can notice that in fact there are many. So for the case of small numbers, the fact that we have a lot of primes up to n is really helpful in finding good colorings. And I finish my talk because I think my time is up. Thank you for your attention.
Thank you. Any other questions for Peter? We had some already.
Yeah, a quick question. So what if so this is perhaps a bit tangential, but what if you're interested in guaranteeing a good coloring? Do you know anything about how many colors you would need?
In fact, a few more should be enough, because you can just take a prime which is slightly larger than n. So this is the trivial kind of construction. So if p is the smallest prime which is larger than n, then p colors are enough. So here a non-trivial result would mean something which beats the prime cap. And I don't know about such constructions. So n plus little o of n is certainly enough. So within a multiplicative factor of 1 plus little o of 1, and colors are enough.
Yeah, thanks.
And Mohammed, you had a question in the chat.
Oh, yes. So to Mohammed's question, no, it's not unique. I had some slides where, so if up to 4 it's unique. For 5 there are 2 good colorings, and for instance, for 6 there are 5 multiplicative 6 satisfactory colorings. So it's not unique.
I thank our speaker again. Peter, if you can log out of your screen share.